The first topic is stochastics of simulation input data. As shown in this table, we can see several examples that is belonging to the queuing models. And they're written in system, and each system is composed of the customers and the server. So later we will study about the configuration of queuing systems, but in this slide, just notice the examples of each systems. For example, in job shop, the customer is mapped to the jobs, and the server is the machines or workers. Also, in the case of the hospital, the customer is patient and the server is nurses or some bed or some surgery equipment can be a server in the hospital. So when we handle these kinds of system, we have to understand the calling population. The calling population is the group of potential customers or product in case of the manufacturing system. Usually, this calling population is a starting point of the simulation. And usually, this calling population is assumed as stochastic distribution, such as number or period of time between arrivals. In this page, some word is not shown. I will upload the modified material after this lecture. The serving time is the period that is consumed by each server. So serving time can be set as time-consuming activity. And serving time of most serving entity has in its inherent variability. In case of even highly automated equipment have their own variability. So the appropriate stochastic distribution have to be defined for the simulation. For example, in the case of bank, the serving time of the clock can be an example of serving time, and with respect to each skill level of each clock, the serving time can be differentiated. So in this case, the serving time of each clock can be modeled as stochastic distribution. Also, the transaction time of automatic transaction machine in bank can be a serving time. And also in this case of the ATM machines, each transaction time may be different with respect to each customer or the type of the machines. So in this case, the transaction time can be modeled as a stochastic distribution. Also, the cycle time in factory or repair time in factory or the consultation time in hospital can be a serving time. And also these kinds of time can be modeled as a relevant stochastic distribution. So now we will see several stereotypes of the stochastic distribution. Those are mostly used in discrete event simulation. First one is Bernoulli distribution. And this before the explanation, I have to excuse some error. The equation is, all the equations are broken in this slide. So please refer the published material in ETL. So Bernoulli distribution is the simplest one of the stochastic distribution. This distribution is just check the pass or fail. So this distribution can be used in some inspection process or the ticket levels. It means the first class or economic class can be modeled as Bernoulli distribution. Next one is uniform distribution. You can see here the type of graph. The parameter of this distribution is two. First one is the minimum value, and second one is maximum value. So this distribution shows the specific range of possible values. In this case, between maximum and minimum values. And in this distribution, each specific values are equally observed. For example, the dice that have the six-sided dice, single six-sided dice can be modeled with this uniform distribution. So usually this distribution is used for the first con modeling when the input data is not well known or the designer of the model have little knowledge of the process. This distribution can be used for the discrete system or also can be used for the continuous system. Next one is the exponential distribution. And this distribution is widely used for some arrival process or the serving time. And this exponential distribution is the number of arrivals that can be expected to arrive during the unit of time. And that time is randomly distributed around the average value. So this distribution have only one parameter, that is the average value. Also, this distribution has the memory release characteristics. It means that in any point of the given value, all the shape or the inclination of in each point have all the same distribution. So this distribution is usually used in Markov process. Actually, this distribution is the same one with the Poisson process. It means that when we define the inter-arrival time or duration, that is matched to the exponential distribution, or when we check the numbers between the arrival times, at the case the Poisson process is defined. So fundamentally, these two distributions have the same distribution, only different in the measures. Exponential distribution has the duration, and whereas the Poisson process is defined as the number between each arrival. So so exponential distribution is mostly used in inter-arrival of customers or inter-arrival of the orders, or the inter-arrival time between breakdown or failures can be modeled as exponential distribution. Next one is the triangular distribution. This distribution is also used when the complete data of the system is not known. This is similar with the uniform distribution, but this distribution is used when the target system is not uniformly distributed. This is different from the uniform distribution. So this distribution has three parameters. First one is minimum value, and second one is maximum value, and third one is most common value. Please note that this M is not the mean value, it's the most common value. It means that if we have to collect the data for the triangular distribution, we have to define M as the most frequently monitored, most frequently measured data. This distribution is not necessarily have to be symmetric. So this distribution is usually used for manufacturing process time or customer service time or travel time. It means that this distribution is usually used for the system that the complete knowledge is not known. And also, mostly this distribution is for the modeling of the server. Next one is normal distribution. And this distribution is widely used for the process that is composed of the several sub-processes. And this distribution has two parameters. First one is mean value, and second one is the standard deviation. And according to the characteristic of the normal distribution, the shape of distribution is, as shown, is described as a symmetric shape. And normally, for normally distributed data, this standard normal distribution can be converted to an actual data value with the following equation, but it is not shown in this slide. Anyway, the normal distribution can be converted to the standard normal distribution that have the mean value as 0 and standard deviation as 1. And if we convert the normal distribution to the standard distribution, then we can use the predefined the numbered template, and that makes the calculation process more easier. The last one is the Poisson process. And as I have mentioned in previous slide, this Poisson distribution is fundamentally same with the exponential distribution. But in case of exponential distribution, the time duration is defined. But in case of Poisson distribution, the random number of events is defined. And if the target system is any kinds of service system, the number of customers in each interval of inter-arrival time, that customer number is defined is following the Poisson distribution. And also distribution has only one parameter. This is defined as lambda, but it is same with the exponential distribution, and that is the mean value. Also, the mean value and various standard, the variance are both equal as the one, not one, as the lambda in this distribution. So the number of arrivals in a given interval of time is the very good example of Poisson distribution. Or if this distribution is applied to the kinds of the batch production system, the number of entities in each batch can be defined as Poisson distribution. So nextly, the stochastics of simulation output. Actually, there is no answer, the exact answer for the definition of the simulation output, because there can be so many kinds of the output definition with respect to the characteristics of each target system. But we can have several stereotypes of the output of the simulation. So first example of simulation output is average system time. It means that the completed time that each entity is in the entire system or in a component of the system. It means that this average system time means the duration, and this duration is the time that each entity have stayed inside of the system. So this time, it can be defined as the service time that is consumed by the server, and the queue time that is consumed in a waiting area, and plus transportation time that is consumed for the movement between each servers. So when we run discrete event simulation, these three kinds of time have to be collected in order to calculate the system time of each entity. And after the collection of all the system time of all the entity, And the average system time can be calculated based on the summation of the system time of all the entity. Second simulation output is average queue time. Queue means those kinds of waiting area. When there is not enough area or enough capacity in the server, in that case, the customer or product have to be stayed in the waiting area. And this waiting area is called as the queue. So queue time means the length of time that each entity waits in a particular queue. And if there are many queues in a model, it makes more sense to calculate the average value of each individual queue. So we will calculate the average queue time in terms of the product or customer, or we can calculate the average queue time of each specific the individual queue. We can say this concept by borrowing the fluid dynamics. It means that there is Eulerian viewpoint and Lagrangian viewpoint. If we think the queue time in terms of each product or each customer, this is the viewpoint. This is coming from the viewpoint of the Lagrangian. It means that the simulation follows each entity of customer. It is a very similar concept of Lagrangian approach, whereas the Eulerian approach is based on the control volume. In this case of queue time with each individual queue, this individual queue can be thought as a kind of control volume. So we monitor or we check the change. No, if we monitor the change of the status of each queue, this can be said as an Eulerian approach. Next simulation output is time average number in queue. The time average number in queue is the number of entities that can be expected to be observed in the queue at any given time. So this is not the confirmed value. This is the chronological data. It means that this time average number in queue is the value of time dependent. Next output is average utilization rate. The utilization means the working time rate of each server. So we have to collect all the working data of each server. And if we divide this summation of working time by the entire simulation time, and then the utilization rate can be calculated. And when in practical case, we have to calculate each simulation output by use of these kinds of the event trace data. So when we implement our own discrete event simulation code, we have to make some class or function that monitor the trains of each attribute of each entities and each customer or product. So in this slide, in one example of the event trace is shown. For example, at time 330, the work start event is triggered. And in this event, the related product or the customer entity is 33, and the relevant process is process 1. And inside of this process, the utilized machine name is process 1 _ 0. Like this, all the events, that is part created or queue entered or work finished, by collecting the older event that is arisen during the running of the simulation, and these kinds of event list can be recorded. And after the completion of the simulation, we can calculate each output by use of these kinds of table. So generally, the simulation engine only record the event and time with product and process information. Then the code have to be implemented required for the calculation of target performance index based on these kinds of table by use of these kinds of tables. Also, we can draw these kinds of Gantt chart by use of the event trace list. Because if we select one specific part in this Gantt chart, this task is mapped to the process name. And with respect to this part, this time is maybe coming from the work start event. And this point of time is coming from work finish. And this data is not shown in this slide, but the relevant, the rated product can be shown like this. So if we collect these kinds of event trace data, then we can draw these kinds of Gantt chart by use of each data of with respect to each event entities. So until now, we have reviewed the input and output for the simulation modeling. Now, let's start the queuing system. Before the go into the queuing system, several basic concepts is reviewed again. The entities in the descriptive and simulation, the entities are something that change the state of the system. So there can be the entity batches. It means that the entity can be a single object, or entity can be batches that have the different size of volume, number, or weight, any kinds of measures. And the entity, it can have the interarrival times, and also entity have their own attributes. So each entity have their own names or values. That is the kinds of the physical ones or and the abstract ones. And there is several kinds of entities. First one is the server. And in our descriptive entity simulation, the server entity is the one that consumes the time. For example, in case of the service system or manufacturing system, this time is the kinds of working. And next entity is the queue. And this queue is the waiting area that where the product or customer can stay. So the product or customer entity waits in this queue area. So mostly this queue is mapped to each server. So if there is enough room or enough capacity of the server, in the case, each customer or product have to wait in the relevant queue area. And the resource entity is the one that serves or supports the service of the server entity. So the worker or machines or any kinds of the moving facility can be an example of resource. So when we make our own discrete event simulation model, the inside of the server code, we can define the require with the waiting function for the use of the defined resource. Again, the several kinds of systems. All these systems can be made as a queuing models. And each system model can have servers and customers. So this is the conceptual diagram for the definition of the queuing model. Firstly, there is a server that consumes time for the handling of each relevant customer or product. And also, each server can have their own queue. It means the waiting area. And this arriving entity is customer or product or part. So anything that those are staying inside of the simulation system can be defined as the arriving entities. And there is also resource. And this resource can be required by the server. So if we define the resource for the server, this server have to wait until the relevant resource is available. And each entity, the arriving entity, can have IAT. It means that inter-arrival time. This time means the stochastic distribution between each arrival times. So if we define this IAT as a time, and this can be defined as the exponential distribution. Or if we define this IAT as the number between each specific duration of time, at the case the Poisson distribution can be defined. And we call the number of the arriving entities in the queue as the queue length. It is a traditional terminology. You don't need to, the reason why this is defined as the length instead of the number. Just use the queue length as the numbers in the waiting area. We can see here the term departure. We just use this word when each entity leaves this server. So those are the usually used when we handle the queuing systems. This is the example for the explanation of the relation with the queue and server. It means that in this case, these three servers are sharing the one single queue. So you don't need to define the queue area for respect to all the servers. According to the case of the target system, you can define the single queue for the multi-server, or you can define the multi-queue with respect to each server. That is following the characteristics of each target systems. Okay. This is just the example for the understanding what kinds of the actual systems in our real life. This bank system, or the bank, can be made as queuing models. It means that each counter can be defined as a server, and this area can be defined as a queue. or waiting area. So in most cases of the actual bank system, there exists multi-servers, and those multi-servers are sharing just one single queue. But sometimes there can be account for the purpose of the custom VIP customer. In that case, there can be its own queue area. So again, the definition of the number of queues follows the characteristics of the target system. Also, these kinds of hospital system can be defined as a queuing model. So in this case, each bed is the server. And outside of this room, there may exist a waiting area that can be defined as the queue. This is the example of the supermarket. And when you frequently visit this kinds of the supermarket, you can see the area for the check the buying the product. And in this case, each counter have their own queue. So in this case, supermarket can be made as a queuing system with the multi-server and multi-queue area. Also, factory can be made as a queuing model. In this case, let's see, it's very complex. Anyway, this is the server where the product is manufactured, and you can see here the relevant resource that is required for the processing of each product manufacturing. And also, in this case of line production, there is no buffer between each the manufacturing process. So in these kinds of the systems, the HQ of the server is defined as a queue with capacity 0. And the last example is our shipyard. Most shipyard can be defined as a very complex queuing models. Let's see, for example, each factory can be defined as the server. And we can see here the waiting area. Those areas can be modeled as the queue. But in this case, the relation between the server and each queue are not one-to-one relation. In this case, the relation between the server and queue have to be modeled as M to N. For example, M with the server and N is not to the Q. So if we are going to define the entire shipyard, in the case very complex queuing models have to be defined. They might be very, very difficult to make as a single model. So in most cases, the shipyard can be splitted into the several components. Such kinds of the fabrication factory or some assembly factory or the external area for the outfitting or painting or for erection, etc. Anyway, ideally, the entire shipyard can be made as a queuing model. Let's skip this slide and jump to this one. So we need to collect the required data in order to define the queuing model. First one is the source of the customers. The customer can be a product in case of manufacturing system, or customer can be the person that those visit any kinds of target system. But we have to define the characteristics of the source as the infinite one or finite one. Infinite means that anyone or anything can use or can be manufactured by the server. So in most cases, the infinite server is used for the simulation. And this simulation is used for the open system. Whereas the finite system is used. A finite source is used for the closed system. It means that the finite number of customers or finite number of products have to be defined, and during the simulation running, this finite number of customer or product can be exist inside of the model. And next one is the arrival rate or arrival time. The interval time can be random number or fixed time. And in case of random number, we can define this random number as the stochastic distribution. And most widely used one is exponential distribution. And if we are going to use exponential distribution, we have to collect the data between the duration between each arrivals. Instead, if we are going to use the Poisson process, we have to collect the numbers between the predefined or fixed duration of time. So again, these two stochastic distribution is fundamentally same. However, the explicit formulation is different because the different measures, difference performance index. Third one is the service rate or service time. Service rate is the number of service being serviced customer or unit time. Or service time can be defined. It means that if we collect the data between the start and finish time of each product in each server, that time can be defined as a service time. So in case of this service rate or service time, the same explanation, the same stochastic distributions can be used. It means that the Poisson distribution can be used for the service rate as the number between its specific durations, or we can use the exponential distribution for the service time between each product's start and finish time. And also we have to check, or we have to define the queue discipline. We call it routing logic. This routing logic is required when there is multiple arriving entities in the queue, and among these multiple arriving entities, and the server is when the server is available, and when we have to define what kinds of entity can be entered to the available servers. In this case, we can use these kinds of the different type of the routing logic. The mostly used one is first comes, first servers. We use this FCFS when there is no predefined routing logic. Or we can use LIFO if this queue is, if the product is accumulated in the queue as a vertical direction. A very good example of LIFO is a steel stockyard in the shipyard. It means that the last entered object is firstly entered into the server. So anyway, these two disciplines are used when there is no specific routing logic. So, or we can also use the random one. But if there is some standard rules for the definition of the routing, we can use these kinds of the queue discipline. Priority means, in order to use priority, each product or each customer have to be defined with the measure of priority. In case of bank systems, I have mentioned the normal customer and VIP customers. If we adjust these priority rules in this bank system with VIP and just the normal customers, the higher priority can be appended to the VIP customers. Or in case of manufacturing system, there can be urgent product that have to be firstly manufactured, In this case, the higher priority can be assigned to this urgent product. So this priority discipline is the example of the routing logic, or we can use SPT, or we can assign the SPT or LPT routing logic. SPT means the shortest processing times. And if we apply SPT discipline to our queuing model, the shorter time product is entered to the server. And contradict the reversely, the LPT means the longest processing time. It means that the product or customer which have the longer processing or longer working time, that entity will be entered firstly to the server. And also there can be so many kinds of disciplines in terms of that can be defined as the routing logics. And also we have to define the capacity of each queue. The queue can have the infinite capacity. In this case, the arriving entities can be stayed in the queue as many as numbers of arriving entities. But if the finite capacity is defined to our queue, in this case, only defined numbers of entities can be stayed in the queue. So these are the data that we have to define in order to make the queuing model. So we are adopt some the notations for the queuing model, and that notation we will follow the Kendall notation. And Kendall notation is a notation according to the various characteristics of queuing models that we have studied in this slide. Kendall has introduced a set of notations at 1951, and this became the industrial or academic standard in the queuing model series. A general queuing system can be defined by 6 notations. First notation in this A is the stochastic distribution of the arrival time. And next one, B, is the stochastic distribution of the server time or working time. And third one is the C, is the number of servers in the system. And mostly, and this is the required the parameters for the definition of queuing model. And remaining 3 parameters, the notation is optional. So first one, T means the maximum number of customers that can be stayed in the system or in the queue. And mostly this D notation is defined as the number of the entities that can be stayed in the entire system. So if we want to know the maximum number of the queue, then we can just use the formula. It means that the if we subtract the server numbers from this entire number D, then we can obtain the numbers, the maximum numbers that can stay in the Q area. And fifth one is E, and this is the characteristics of calling population. If we denote this calling population, default value is the infinite. Also, this number D is also default value is infinite. And the last one is the F, and F means the Q disciplines. So if any specific kinds of routing logic is defined, that routing logic or queuing discipline can be noted, can be described as this location F. Then if we follow this candle rotation, the simplest one is this MM1. Commonly, this MM1 is called as a Markovian process because any queuing models that have the arriving process with the exponential or Poisson process, that queuing model is called as a Markovian process. Anyway, this simplest queuing model, MM1, is the one that have the exponential and exponential serving time. And this model has only one server. So this is a very, very simple example. That can be one server, and this server has single queue, and there is not shown the queue capacity and also the calling population. So the arriving entities are infinite. Also, the characteristics of this queue is also infinite. So if we do not denote the D, E, and N, the default value is infinite arrival entities and infinite capacity queue.